Okay, I am back for the third in the series of 3 videos on limits. And without further ado, let's jump right in. Limits part 3, written in French, I may add. The existence of a limit. If the limit as x approaches a minus of f of x is equal to the limit as x approaches a plus of f of x, then the limit of the function exists at x equal a. That is, the limit as x approaches a of f of x exists and is equal to L. Let me dive into that a little bit more. What does it mean when we say the limit as x approaches a minus of f of x as opposed to the limit as x approaches a plus of f of x? Well, you may have a function, and let's say this value is x equal a. The limit as x approaches a minus of f of x, if this is f of x, that means you're finding the limit as x is approaching a, but from the left of a, from a value of x that's a little less than a. And you can see as x is approaching a from the left, the function is approaching this value right there. The limit as x approaches a plus of f of x, that means you find the limit as x is approaching a, but from the right of a, from the right side of a. You're coming towards a, but from the right of a. And again, in my specific example, you can clearly see that the function is also approach as x is approaching a from the right. The function is approaching that same y value right there from both sides. And what we were saying is that the limit exists if the limit is x, if the function is approaching the same value as x is approaching a from both sides, then the limit exists. No, so that's a very technical concept, and we're going to go through several different examples that drive that point home. Right? So that's all that means. The limit as x approaches a minus of f of x means you find the limit as x is approaching a from the left, and the limit as x approaches a plus of f of x means you're finding the limit as x is approaching a from the right. Okay. Note, let me read it over again. If the limit as x approaches a minus of f of x is equal to the limit as x is approaching a plus of f of x, then the limit of the function exists at x equal a. That is, the limit as x approaches a of f of x exists and is equal to some value L. There's a special note at the bottom there that says L may not be the same as f of a. As you will see as we are going through some more of the examples, L may not be the same as f of a. L is equal to f of a only if f of x is continuous at x equal a. So the limit and the value for the function may or may not be the same. That's what that's saying. Okay, so that was for the existence of a limit. How about the non-existence of a limit? The limit of a function does not exist at x equal a if any of the following hold. If the limit as x approaches a minus of f of x is not equal to the limit as x is approaching a plus of f of x. How is that possible? Well, it's possible because sometimes a function may look something like this. This is a. On the left of a, the function might come to this point. This is a. And from the right, I'll have an open circle, and the function continues like that. You can see as x is approaching a from the left, the function is approaching this value down here. And as x is approaching a from the right, the function is approaching a different value. This function, by the way, is discontinuous. So that's why the function is not approaching the same value from both sides. Right? So that's a situation that can occur. Let me get rid of all this scrappy stuff. That's just to explain in a little more detail. Okay. Right, so the limit of a function does not exist at x equal a if the limit as x approaches a minus of f of x is not the same as the limit as x approaches a plus of f of x. And b, the limit does not exist if f of x increases or decreases infinitely. That is, the function has a vertical asymptote. You'll see in several of the examples as I'm going to do a little later on. And if f of x oscillates infinitely, example, sin x oscillates between plus and minus 1 as x is approaching plus or minus infinity. Therefore, the limit as x is approaching infinity of sin x does not exist. Does not exist. Okay, what's the next part? Let's talk about continuity. If a function f of x is continuous at x equal a, three conditions must hold for a function to be continuous at x equal a. The limit must exist, right? The limit of the function must exist, and we saw what's required for the limit to exist. The limit as x approaches a minus of f of x has to be equal to the limit as x approaches a plus of f of x. You must be approaching the same value from both sides. So, for the function to be continuous, the limit must exist. The function must be defined at x equal a. That is, f of a must be defined. And the limit as x approaches a of f of x must be equal to f of a. Again, that's going to come out with the examples we're going to look at a little later on. Note, if a function f of x is continuous at x equal a, that means that the limit exists. However, if the limit exists, that does not necessarily mean that the function is continuous at x equal a. Once the function is continuous, automatically that means the limit exists. But if the limit exists, that on its own is not enough to tell you that the function is continuous at x equal a. As you just saw, there are three criteria that must be satisfied for you to conclude that the function is continuous at x equal a. All right, so let's get to the examples. First major example here. I have a function, f of x, y equal f of x. There. And I'm trying to see what's happening at x equal a. Now let's see. The limit as x is approaching a. I'm reading the script that I already have there. The limit as x is approaching a of f of x exists. Why is that? Because as you can clearly see, as x is approaching a from both sides, as x is approaching a from the left, and as x is approaching a from the right, the function is approaching the same value from both sides. And that value I call L. So the limit exists. The function is approaching the same value from both sides. The limit exists. F of a also exists. Right? The function is defined at x equal a, so f of a exists. F of a happens to be the same as L, which is the limit. And the third part says exactly that. The limit L is equal to f of a. Once those three conditions are met, I can conclude that f of x is continuous at x equal a. All right, let me go them over again. The limit as x is approaching a of f of x exists. How do I know the limit exists? Well, graphically I can see that. But mathematically, you have to prove that the limit as x is approaching a minus of f of x is equal to the limit as x is approaching a plus of f of x. And they're both approaching the same value from the left and the right, and that value is L. F of a exists, and f of a is equal to L. Once those three conditions are met, I can conclude that the function is continuous at x equal a. All right, so that's one scenario. Let's look at the next case. Notice the fundamental difference between this function and the first function and this second one I'm about to look at. Looks like there's a big hole in the function when x is equal to a. All right, so let's see. The first condition, the limit as x is approaching a of f of x exists. The limit exists since the limit as x is approaching a minus of f of x is equal to the limit as x is approaching a plus of f of x, which is equal to L. Please remember, I think I stressed this in the previous limits videos as well. The limit represents the value the function approaches, not necessarily the value the function ultimately gets to when x gets to a. Because as you can clearly see, when x gets to a, there's a hole in the function there. There's no value for y at when x is equal to a. But clearly the function, the function is approaching L from both sides. It's the same value from both sides, right? Let me shade that in red. When x is approaching a from the left, the function is approaching that hole, as you can see there. Similarly, the function is approaching the same value from the left. The limit exists if the function approaches the same value from both sides, even if the function never actually gets to that same value. And clearly in this case, the function never gets to that y value because there's a hole in the function right there. But the limit still exists because the function is approaching the same value from both sides. So that's the first condition that's met. The limit exists. Second condition, f of a does not exist. Why? Because there's a big hole in the function. The function is undefined when x is equal to a. What's my conclusion? My conclusion, written right here, says that f of x is discontinuous at x is equal to a. And the point on the function where x is equal to a, that point is called a point discontinuity, or a hole. Just as it shows up in the function there, it looks like a hole in the function. Y doesn't exist at that point, but the limit exists. All right, so make sure you understand that subtle difference. Let's go to the third one. This one is interesting. The limit as x approaches a of f of x exists. Why is that? Because the function approaches the same value from both sides as x is approaching a. Look, as you can clearly see, as x is approaching a from the left, y is approaching L, even though you never quite get to L. And as x is approaching a from the right, the function also approaches the same value L, even though it never gets to that value L. So the limit exists. The limit exists once the function approaches the same value from both sides. So that's the first part. F of a also exists. As you will notice, f of a, you see this big black dot up here? That's the value of the function. And f of a happens to be different from the limit. F of a is actually, as I showed there on the graph, it's some value p that I refer to as p. So the limit exists because the function is approaching the same value from both sides as x is approaching a. F of a exists. F of a exists because that's where I have the value of the function above the value of L. But in this case, the limit, which is L, is not the same as f of a. There are two distinct points. F of x, again, in this case, is discontinuous at x equal a. And this, again, is called a point discontinuity. Notice the fundamental difference between this scenario up here and this one that we just looked at. Both of them have a hole in the function where x is equal to a. But in the one above, f of a does not exist. The y value doesn't exist. But in this one below, the y value does exist. The y value is p. But the y value is at a different point from where the limit is. Okay. Let's look at the next scenario. You can clearly see the limit in this case does not exist. And we can give several reasons for that. One, it is clear that as x is approaching a from the left, the function is approaching minus infinity. Look, the function turns and goes to minus infinity. And as x is approaching a from the right, the function turns and goes to plus infinity. So you're clearly approaching two different y values as x is approaching a. So for that reason alone, you can say that the limit doesn't exist. However, this is an infinite discontinuity, as we saw above. Let me show you back again. If the function here, right there, if f of x increases or decreases infinitely, then the limit doesn't exist. And that's exactly what's going on in this example. The function is increasing and decreasing infinitely. So the limit doesn't exist since f of x is increasing and decreasing infinitely as x is approaching a, and f of a does not exist. F of x is therefore discontinuous at x equal a. This one is called an infinite discontinuity. I'm not going to be able to get rid of these red marks. Hope so. All right. Let me not spend too much time on that. All right. Infinite discontinuity in this case. And the limit doesn't exist. Same here. The limit as x approaches a of f of x does not exist since f of x increases infinitely as x is approaching a. It's increasing infinitely on both sides as opposed to the one above where it was increasing infinitely on one side of a and decreasing infinitely on the other side of a. This one is increasing infinitely on both sides of a, but once it's increasing infinitely or decreasing infinitely or increasing and decreasing infinitely, then the limit does not exist. F of x is discontinuous at x is equal to a, and this again is called an infinite discontinuity. This is my favorite. This one right here. This is the last one. You can clearly see that as x is approaching a, let me read what I have there first. The limit is x approaching a of f of x. That limit does not exist since the limit as x is approaching a minus of f of x is not equal to the limit as x approaches a plus of f of x. You can clearly see that as x is approaching a from the left, the function is approaching that hole, that value q, where you have that hole. And as x is approaching a from the right, you can see the function is approaching a different value. The function has to approach the same value from both sides of a, from the left of a and from the right of a, must approach the same value for the limit to exist. So this is by just observing the graph, you can tell that the limit doesn't exist. Okay, so the limit doesn't exist because you're approaching two different values from the two sides of a. F of a exists, f of a does exist. And if you notice, f of a is the value p because, do you know why? Let me give you a second to think about it. Let me get rid of these red marks. Because the only value that the function gets to when x gets to a is up here, right up there. So it's not like I couldn't have a solid dot here as well. Could not. Here. If I'd put a solid dot there, that would be a contradiction. Because the function wouldn't know which value to take on when x gets to a. So that's why one of them had to be an open circle. So therefore, the function takes on a value of q, that higher value, when x is equal to a. So f of a exists and is equal to, did I say q? I meant p. F of x exists and is equal to p so f of a is equal to p. F of x is discontinuous at x is equal to a, and this is called a jump discontinuity. The function that kind of separates into two different parts from the two different sides, and the function will be discontinuous. So all of those ideas, continuity, discontinuity, limit existing, limit not existing, the function existing at x equal a, the function existing at x equal a, the function not existing at x equal a, all of those ideas are put together in these graphical representations. Okay. This is just some scrap I was playing around with before I actually drew those graphs. All right, why don't we start working on some of the problems that I set forth underneath here. What's this? All right. So here's our first problem. You're given that f of x is equal to 2x plus 3 for x greater than 1, and f of x is 6x minus 2 for x less than or equal to 1. Sketch the graph of f of x. So that's the first thing we're going to do. Let's set that up. Let me see if I can draw a proper graph. So yeah, these are my axes. I'm gonna try to guesstimate for the most part a scale. So, and we are interested in what's going on at x equal 1. So let's say x is equal to 1 is somewhere there. Ooh, gosh. Let's say x is equal to 1 is somewhere there. So I'm going to draw a vertical line through that point. I need a straight edge. Good enough. This is x is equal to 1. Good. What does the function look like on either side of 1? Okay. Well, it's 2x plus 3 for x greater than 1. And 6x minus 2 for x less than or equal to 1. So it's the 6x minus 2 that includes the x equal 1. So somewhere I'm going to have a solid dot associated with that point. So I'm going to plug in into the 6x minus 2. I'm going to plug in x is equal to 1. So when x is equal to 1, 6x minus 2 is 4. When it's equal to 1, the y value is 4. 1, 2, 3, 4. Let's say somewhere there with a solid dot. And I'll pick another value less than 1. When x is 0, y is minus 2. When x is 0, y is minus 2. Okay. So that would be here somewhere. And I have a straight line passing through those 2 points. Let me actually draw my lines in a different color. I'll put it in red. There. Good. So this is the part of the graph that exists when x is less than or equal to 1. The corresponding y value here, coordinates there. This is 4, right? When x is 1, 6, 1, 6. Minus 2 is 4. And when x is 0, y is minus 2. This point here is minus 2. And let's sketch the other half. When the first part, f of x is 2x plus 3. Now, even though x is not equal to 1, I'm going to actually substitute x is equal to 1 into there, but I have to put an open circle to indicate that the function doesn't quite exist there. So when x is 1, 2 1s, 2 and 1, 2, 1, ooh. 2 1s, 2 and 1 is 2 1s, 2 and 3 is 5. So the y value here is 5. Open circle. And when pick any value greater than 1, let's say I'm going to put x equal 2. I'll make it 2 2's 4 and 3 is 7. Oh, so when x is 2, y is 7. So somewhere up here. So that other half does this. All right, notice, let me come straight down here. Right, this value here is 5. Good. I'm supposed to put this part in red as well. You guys are wasting time, huh? There. All right. All right, leave it. So that's the graph. Okay, so let's see if we can answer the questions. Sketch the graph, that's the graph, and I showed clearly what happens. We have the function x is equal to 1. The portion of the function to the left of 1 exists from 1, and it goes downwards. Portion of the function to the right of 1 doesn't actually get to 1, but it increases beyond 1 for values of x that are greater than 1. So that's the sketch. Find the limit. So find the limit as x is approaching. I should put it in right here. The limit as x approaches 1 plus of f of x. That means you're approaching 1 from the right of 1. And it's clear to me that when you're approaching from the right of 1, the function is approaching 5. It never quite gets to 5, but it approaches 5. So that limit is 5. As you're approaching 1 from the left, the limit as x approaches 1 minus of f of x. Right. That means you're approaching 1 from the left. If you're approaching 1 from the left, the function is clearly approaching 4. Now, here's a classical example that shows what the limit is all about. When you're approaching from the left, the function approaches 4 and actually gets to 4. So the limit is 4. When you're approaching from the right, the function is approaching 5, but it never gets to 5. But the limit is still 5 because the limit is the value that the function approaches. I can't stress that point enough. So there. And it is clear that because the function is approaching two different values, as x is approaching 1 from the left and from the right, that means the limit does not exist. So let's see if we can answer the rest of the question. Does the limit as x approaches 1 of f of x exist? And you have to give it a reason. So no, the limit does not exist. No, the limit does not exist, since the limit as x approaches 1 plus of f of x is not the same as the limit as x approaches 1 minus of f of x. The limit does not exist. The second part, is the function defined at x is equal to 1? Yes, the function is defined at x is equal to 1. When x is equal to 1, the function has a value of 4. Not 5, because the function never gets to 5. So the function is defined. This is yes. This one there, that's a yes. The function is defined at x is equal to 1. And the value is f of 1 is equal to 4. And then the last part, is the function continuous at x is equal to 1? Well, certainly one of the criteria has not been met. In fact, two of the criteria have not been met to be continuous. But any one of them that's not met would tell you that the function is not continuous. One of the first criterion that had to be met was that the limit as x is approaching 1 plus had to be equal to the limit as x is approaching 1 minus of f of x. So based on that alone, we can say f of x is not continuous at x is equal to 1, since the limit as x is approaching 1 plus of f of x is not the same as the limit as x is approaching 1 minus of f of x. Okay, so that addresses that first question. There's another question I want to visit. The testing is testing these same ideas. Let's look at that one. Find the limits as x is approaching minus 2. No, don't. Please don't confuse minus 2 with 2 minus. Minus 2 is the negative number. 2 minus means you're approaching 2 from just before you get to 2. 2 plus means you're approaching 2 from the other side, just before you get to 2 from the right. Don't confuse those things. All right, so the limit as x is approaching minus 2 of that function. This looks like if you plug in the minus 2 directly, it's going to be 0 upon 0, but we can check it. The limit is equal to, let's see what it'll get. It'll be minus 2 squared plus 5 times 2 plus 6 all over 2 squared minus 2 minus 6. Plus a minus 2. I messed this whole bottom part up. I messed the whole thing up. Let's try this again. This is equal to minus 2 squared plus 5 times minus 2 plus 6 all over minus 2 squared minus a minus 2 minus 6. Okay, on top I have 4 and 6, 10 minus 10, that's 0. On the bottom I have 4 and 2 is 6 minus 6 is 0, undefined. Everybody knows what you do at this stage. You factorize, and I kind of factorized it beforehand. You should double check the factorization. X squared plus 5x plus 6 is x plus 2 times x minus x plus 2 times x plus 3. And x squared minus 5, x squared minus x minus 6 is x minus 3 times x plus 2. So it looks like the x plus 2's will cancel out. And we're left with x plus 3 upon x minus 3. And therefore the limit as x is approaching minus 2 of x squared plus 5x plus 6 upon x squared minus x minus 6 is now the same as the limit as x is approaching minus 2 of x plus 3 upon x minus 3. And that would give you minus 2 plus 3 upon minus 2 minus 3. On top I'll have 1, on the bottom I'll have minus 5. So finally, the limit as x is approaching minus 2 of x squared plus 5x plus 6 all upon x squared minus x minus 6 is negative 1/5. Yay. You should be able to do that though, with no problems. Let's check the next part. You have a function f of x. A function f on R is defined by f of x is equal to x squared plus 1 for x greater than or equal to 2 and bx plus 1 for x less than 2. Great. Find f of 2. Well, for me to find f of 2, I can only substitute x equal to into the part of the function where the function actually exists when x is 2. And clearly it has to be this first part. Right there. That's the only part of the function that exists when x is equal to 2. Okay? So, f of 2 is equal to 2 squared plus 1, which is 5. The next part says find the limit as x is approaching 2 plus of f of x. Well, the limit is x approaching 2 plus, which means you're approaching from values to the right of 2. You're coming in from right to left. So the limit is x approaching 2 plus of f of x. is equal to, you simply plug in 2 into that portion of f of x, that's the limit, as x is approaching 2 plus of the x squared plus 1. And that would be 2 squared plus 1, which is also 5. The limit is x approaching 2 minus. This is a 2 plus here, by the way. That's the plus and that's a minus. The limit is x is approaching 2 minus of f of x in terms of the constant b. Well, the limit is x is approaching 2 minus of f of x. That's equal to the limit as x is approaching. Can't write the approaching sign. Limit as x is approaching 2 minus of the bx plus 1. And the value there is 2b plus 1. And then they want the value of b such that f is continuous at x is equal to 2. But for the function to be continuous at x is equal to 2, 3 conditions must hold. First of all, the limit as you approach from the left must be equal to the limit as you approach from the right. So to be continuous, at x is equal to 2, the limit as x is approaching 2 plus of f of x must be equal to the limit as x is approaching 2 minus of f of x. As you're approaching 2 plus, the value is 5. As you're approaching 2 minus, the value is 2b plus 1. What does that make b? Throw the 1 divided by 2, b equal 2. So that condition alone would simply mean that the limit exists. The other 2 conditions that must hold was that the function is defined at x is equal to 2, and it is right there. The value is 5. And the third condition that should hold is that the value of the function must be equal to the value of the limit, and it is. Right, the value of the limit. The limit is approaching 2 from the left, and it's approaching it's approaching 5 from the left, and it's approaching 5 from the right. And therefore the limit does exist and is equal to 5. Well, the only thing they ask for there is the value of b, so that the function is continuous at x equal to 2. But we found it. It's right there. All right, let's try the next question. Find the value of x for which that function is discontinuous. A rational function of that nature is discontinuous for the values of x that make the denominator 0. That's where you have the vertical asymptotes. So let me start setting that question up. All right, the function is x cubed plus 8 over x squared minus 4. X cubed plus 8 over x squared minus 4. The given rational function is discontinuous at the values of x which make the denominator 0. That is, it is discontinuous at the vertical asymptotes. So if we set the denominator is equal to 0, x squared minus 4 is equal to 0. You can either difference the squares or throw over the 4. I'm choosing to do difference of squares. X minus 2 times x plus 2 is equal to 0, which makes x equal to 2 and x is equal to minus 2. Right? F of x is discontinuous. at these values of x. So that answers the first part. The second part is, hence or otherwise, find the limit as x is approaching -2 of the same function. Well, all we have to do, we know it's going to be discontinuous at that point. So very likely you'll end up with 0 over 0. Let's see. The limit as x is approaching, I think they said -2. Yes. As x is approaching -2 of x cubed plus 8 upon x squared minus 4. Let's see if I plug in -2 cubed plus 8 upon -2 squared minus 4. That's -8 plus 8 over 4 minus 4. 0 upon 0, undefined. And since it's undefined, then you have to use one of the methods we established earlier to set it up. So this becomes the limit as x approaches -2. We got to factorize the numerator. That's the sum of two cubes. And I think off the top of my head, that would be x plus 2 into x squared minus 4x plus 4. Let me see. X plus a into x squared. That probably is minus 2x. X squared minus ax, and a is 2. Yes, this is 2 plus a squared. I'm pretty sure that's correct. Oh. And in the denominator, I will have factorize x minus 2 times x plus 2. And what cancels out? The x plus 2, right? X plus 2 goes, so that becomes the limit as x approaches -2 of x squared minus 2x plus 4 upon x minus 2. Excuse me for a second. Yes, okay. And you plug in the x equal -2. So that becomes -2 squared minus 2 times -2 plus 4 on the bottom -2 minus 2. What does that look like? This looks like, what does it look like? 4 plus 4 plus 4 upon minus 4. That's a 4, that's a plus, and that's a plus 4, yes. 4 3 is 12 upon minus 4, which looks like a -3. Oh, what do you know? So therefore the limit, if I were to conclude there, the limit as x approaches -2 of x cubed plus 8 upon x squared minus 4, that's -3. All right. And I have number 15 in there. I'll let y'all do that. What else was there in that problem? By using the fact that the limit as x approaches 0 of sine x over x is 1, or otherwise, find the limit as x is approaching 0 of 2x cubed plus 4x the limit as x is approaching 0 of 2x squared plus 4x all upon 2x cubed. Yes, all upon sine 2x. Sine 2x, like so. Okay, so how do we handle this? One thing I would want to do, I would divide both numerator and denominator by 2x, because I got the sign 2x. If I got 2x on the bottom of the sign 2x, looks like I'll be good. So this would be equal to the limit as x is approaching 0 of 2x cubed plus 4x all upon 2x all upon sine 2x upon 2x. That looks good. Looks good to me. And then I split it into a numerator limit and a denominator limit, right? Using the laws of limits. The limit as x is approaching 0 of 2x cubed plus 4x upon 2x all upon the limit as x is approaching 0 of sine 2x upon 2x. In my numerator, I can factor out a 2x and cancel out with the 2x on the bottom. So this is the limit as x is approaching 0. 2x comes out. What's left inside? X squared plus 2, I think. Double check. 2x cubed and 2 2's 4x. Yes. Upon 2x all upon the limit as x is approaching 0 of sine 2x upon 2x. This 2x will cancel with that 2x. One more line. That becomes the limit as x is approaching 0 of x squared plus 2 all upon the limit as x is approaching 0 of sine 2x upon 2x. And now I can plug in x is equal to 0 to give me 0 squared plus 2, and in the denominator plus 2. And in the denominator, the entire limit is 1. Y'all know that by now. So this limit just gives me 2 overall. That looks pretty good. Next part. The function f on r is defined by f of x is x squared plus 1 for x greater than 1. F of x is x squared plus 1 for x greater than 1. And what's the other piece? 4 plus bx for x less than 1. Okay. Find the limit as x is approaching 1 minus of f of x. The limit as x is approaching 1 minus of f of x. Well, which one of these two functions exists to the left of 1? It has to be the 4 plus the px, right? That function exists for values of x less than 1. So you can approach 1 from values of x less than 1. So this would be the limit. By the way, one of the first things I noticed is that the function is not defined when x is equal to 1. It's defined for x greater than 1. It's defined for x less than 1, but it's not defined for x equal to 1. So that's one thing that I noticed up front. The limit as x is approaching 1 minus of f of x is equal to the limit as x is approaching 1 minus of the 4 plus bx, which would be, just plug in the 1 in there, you get 4 plus p times 1, which is 4p. What's wrong with my math all of a sudden? 4 plus p times 1 can only be written as 4 plus p. Thank you, Mr. Carroll. What's the next part? The value of the constant p, such that the limit as x is approaching 1 exists. Yes, the limit would exist even though the function is not defined at x equal 1, as long as the function is approaching the same value from both sides. So what I'm going to do, I want to find the limit as x is approaching 1 plus of f of x, which is equal to the limit as x is approaching 1 plus of In this case, it'll be the x squared plus 1, because x squared plus 1 exists for values of x that are greater than 1. So you can only approach 1 from values of x that are greater than 1 if you're finding the limit as x is approaching 1 plus. We're going to substitute 1 in there. That would be 1 squared plus 1, which is 2. And if the limit, for the limit to exist, let me make sure I get the language right. The value of p such that the limit of x approaching 1 exists. So if the limit as x approaches 1 of f of x exists, that would mean that the limit as x is approaching 1 plus of f of x would have to be equal to the limit as x is approaching 1 minus of f of x. And therefore the 4 plus b, ooh, what's going on there? And therefore the 4 plus b would have to be equal to 2, right? Limit is, the 2 is for the 1 plus, and the 4 plus b is for the 1 minus. The 2 must be the same, which makes p equal minus 2. And now that we have that value, hence determine the value of f of 1 for the function to be continuous at x equal 1. Well, first of all, the function doesn't exist at x equal 1. But if it were to exist, f of 1 would have to be the same as the limit. F of 1 would have to be the same as the limit. And the limit is 2. Right? If I put p equal 2 in here, minus 2 in there, I'll get 2. From the left, it's 2. The limit is x. So the limit as x approaches 1 of f of x is 2. It's the same value you're approaching from both sides. And also f of 1 must be equal to 2 if f of x were to be continuous at x equal 2. And I'm done with that. All right, so I got several of the example problems that I wanted done in there. I also explained all the subtleties about functions being continuous, discontinuous, the limit existing, the limit not existing, and all the other stuff. The function existing at x is equal to a, the function not existing at x equal to a, the function having one value when you approach from the left and a different value when you're approaching from the right. So this is a very subtle video. You might want to look it over more than once before you get the hang of all those subtle points. And then the example problems, especially the ones with either with the graphs or this last one. The one in the middle is not so, well, at least the first part isn't. But these are very interesting problems that bring those points out. And then for your homework, I have an exercise right here. This is from our standard text. This is your worksheet. Right, you can work on that. And I'm sure you'll become better at this part of limits when you're done with that. All right, I'm done with this video, and yeah, you might see me again for another video and maybe some other topic. But for now, I'm out. Bye.